Okay, can you hear me? Okay. 오케이. 그 OBS에서 핑이 보이는데 그 핑이 여전히 그 레드 핑이에요. 원래 속도가 좋을 때는 그린, 그다음에 조금 불안할 때는 뭐 주황색, 속도가 완전히 느릴 때는 빨간색인데 지금 완전히 계속 빨간색 핑 상태예요. 그래서 뭐 연결이 그렇게 좋은 건 아닌 것 같은데 그래도 한번 해보도록 합시다. Okay, so today we will talk about organometallic chemistry. In next class, we have learned about CO ligand, CO, carbon monoxide. So, as we learned that the carbon monoxide can make strong binding with transition metal because carbon monoxide can give electron by using sigma group, so sigma donor, and CO, carbon monoxide, can get electron from the transition metal pi back bonding. So they can make strong interaction between transition metal and carbon monoxide. So today we will talk about pi ligand. Pi ligand is it's kind of a unique ligand. Okay, so if you look at the pi ligand, so pi ligand can two types of pi ligand can be possible. For example, okay, this type pi ligand is linear pi ligand. This type is cyclic pi ligand. So linear pi system, pi ethylene is just this type. So ethylene can coordinate to transition metal by using their pi orbital. Pi. So p orbital can overlap each other. They can make a new pi molecular orbital. This molecular orbital can coordinate to transition metal. And pi allele system is kind of like this. This is pi allele system. So I draw the 1 line, but 3 carbon can coordinate to transition metal by using this. So we will learn why this type of ligand is important. So if you think about why we are talking about organometallic complex and why we are talking about the CO ligand and pi ligand, the important purpose is to understand organic reaction using transition metal. So if double bond or allele can coordinate to transition metal, some nucleophile can attack this carbon to make something. So these nucleophiles can attack this carbon or this carbon. So due to the coordination of transition metal, the nucleophilic attacks are possible. So without transition metal, the nucleophilic attack is not easy, but by using coordination of transition metal, the nucleophilic attack is possible. Today, okay, let's talk about linear pi system. The first example of pi complex is Diaz salt. So, if you look at the Diaz salt, you can see platinum here and ethylene gas is here. Ethylene gas coordinate to platinum. So, like this. So, if you want to know how the ethylene coordinates to transition metal, so this ethylene can give the transition metal by using pi orbital. So these pi orbital can give the electron to transition metal, like sigma donor. But if you think about pi star orbital should be like this, because pi star orbital is the antibond of 2p orbital, and transition metal has d orbital like this. So these empty pi star orbital can receive the electron from the transition metal like this. So similar to carbon monoxide, the double bond can act as a sigma donor and pi acceptor. So this pi system, pi ligand can make good coordination to transition metal. Okay. So just the free CC double bond is about 133 bond lengths, but if double bond coordinate to transition metal, the bond length is 137. Why? Because transition metal give the electron to pi star orbital, so the double bond get the electron density to pi star orbital. So the bond strength should be weakened. So bond strength weakened means the bond length is elongated to longer. Okay. How about sigma donor? So the filled pi orbital gives the electron, and empty pi star orbital get the electron. So strong binding. Okay. Okay, how about pi allele system? Pi allele system. So actually, allele is like this. However, if you think about the resonance of allele, you can easily figure out this allele have resonance structure. Like this. So because allele has this resonance structure, we usually draw the allele structure like this. Total minus. So this allele has -1 charge, but we don't know which carbon has -1. Maybe minus evening -1/2, -1/2, total -1. And the all pi orbitals, the perpendicular pi orbital, p orbitals are conjugated. So these p orbital can act as a ligand. So if you look at the pi allele system, so nickel can have two pi allele system. So as you can see, we usually draw like this, nickel and like this, palladium like this. So this should be ethylene, double bond and anion. So how? So if you look at the allele molecular orbital, the molecular orbital of allele group, so pi neutral, and pi star. So please remind in organic chemistry, the aromatic. So when if you think about aromatic system, we draw some molecular orbital like that. So pi neutral, and pi star. So pi is all p orbitals are same direction. So black, 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 white, white, white. So all all p orbitals are overlapped each other. Neutral is one node, and pi star is two nodes. But the p orbital can coordinate to pz orbital, and pi neutral can interact with py orbital with metal, and pi star also can interact with the dxz orbital. So these interaction make strong interaction between transition metal and allele. So The reaction is very simple. If you have metal carbide complex, is that we have learned that metal carbide complex is the compound consisted of transition metal and only carbon monoxide. So these compounds usually act as a precursor for other synthesis. So we usually use this precursor. And then if you add propyl chloride, then chloride kick out and allyl is generated. Allyl to coordinate to manganese. And then if you heat it up, carbon monoxide is detached to generate stable complex. You can calculate the electron from this. Okay, do you understand? But I will not calculate electron anymore in class. But you can do that. 그러니까 앞으로 제가 일렉트론 카운팅을 하면서 설명하진 않을 거예요. 근데 여러분들이 직접 해보면서 이래서 반응이 잘 갈 수 있겠구나. 이래서 반응이 뭐 안 가겠구나. 뭐 이런 식으로 한번 해보면 되겠습니다. Okay. So, I want to talk about other linear pi system, such, for example, COD. COD is very famous ligand, cyclopentadiene. For example, if you search the transition metal complex in Aldrich, you can buy this complex because some of these complex is very stable. Some of these complexes are very stable, so you can buy from the Aldrich or Alpha something. So if you look at this compound, this transition metal is very, very useful to make CC bond formation or asymmetric some reaction. So as you can see, rhodium has two cyclooctadiene. So cyclooctadiene, 1,5-cyclooctadiene, it has two double bond. These two double bond coordinate to transition metal to make complex. Okay. So we usually say just COD. It means cyclopentadiene. Okay. So butadiene also can make coordination, but if you look at the butadiene, S-cis butadiene and S-trans butadiene can make coordination. How about other? Like this, COD here. 1,3 COD is here. So if you look at the butadiene has pi, anti. But all MOs can interact with transition metal because transition metal has d orbital. So now you can understand, because of d orbital of transition metal, many different type of coordinations are possible. So butadiene, cyclooctadiene are good ligand for transition metal. Okay, cyclic pi system. We know that the representative example of cyclic pi system is ferrocene. Ferrocene has CP. CP means cyclopentadiene. anion. So we usually draw like this. We have learned that cyclopentadiene is aromatic because generally Huckel's rule 4n plus 2 rule, so generally 2, 6, 10 is aromatic. But if you think about cyclopentadiene anion, it has only 5 p orbitals but 6 electrons. So we know that this is aromatic. Cyclopentadiene is aromatic. Anyway, so this cyclopentadiene anion ligand can act as eta 1, just metal coordinate here, eta 3, 1, like allele system, 1, 2, 3. But generally eta 5, all carbons connect to transition metal like this. Most general case is eta 5. So ferrocene interact with 2 anionic Cp to make ferrocene. So if you want to understand the ferrocene, you need to figure out the MOs of two cyclopentadiene ligand. Okay, in this case, transition metal is here, so all p orbitals directions are to transition metal, so opposite direction. But in this case, same direction. In other words, this is the p orbitals are pointed each other. But in this case, so same direction. I mean, because there is an opposite sign, I think you would be confused if I same direction. But I think you can distinguish it. This same, this opposite. Okay. So if you draw the all MO pairs, so stable, 그러니까 zero node, if you think only one cyclopentadiene, you can draw only 5 MOs. But we are thinking two cyclopentadiene, so you need to think couple. Same direction, opposite direction, same, opposite, same, opposite. Do you understand? So if you think only one MO, only one cyclopentadiene, just you think this. But we have couple of cyclopentadiene, so we need to consider same, opposite twice. So all cases like this. But energy level is same because node is 1, 2, 1, 2 like this. Anyway, so it is very complicated, but if you think about the MO of cyclopentadiene and d orbital of transition metal, so in this case it's bonding, but in this case anti-bonding. Do you understand? So we can draw all of interaction of ferrocene. So you don't need to do all of interaction. I mean, conceptually you can understand, but you don't need to do it by yourself. I want to say in Korean. 그러니까 여러분들이 이 MO를 이해만 하면 되지 MO를 다 그릴 필요는 없어요. 그러니까 이렇게 생각하면 돼. 사이클로펜타다인이 2개 있으니까 뭐 노드가 0개짜리도 2개 그려야 되고 노드가 하나짜리도 2개 그려야 되고 또 다른 하나짜리도 또 2개 그려야 되고 2개짜리도 또 2개 그려야 되고 2개짜리도 또 2개 그려야 된다. 뭐 이건 이해됐죠? 그 다음에 각각의 d 오비탈을 넣어서 이게 본딩, 엔티본딩이 모든 경우의 수가 생길 수 있다. 이 정도만 이해하면 되지 이걸 다 막 해가지고 그려서 할 필요는 없어요. 그건 다 뭐가? 컴퓨터가 해줄 겁니다. 그러니까 여러분들 그런 거 할 필요는 없고 그 대신 이제 그렇게 모든 인터랙션을 해서 나온 결과가 요거구나 라는 것만 이해하면 돼요. 이해하시겠죠? Okay, so you need to understand you don't need to draw all of interaction, but just you need to understand conceptually. Okay, conceptually. Okay, then if you think about the interaction, so ferrocene is here and group orbital is here because of 2 cyclopentadiene. So these are new MOs, new MO. Okay. So here is DG square, something. So if you look at this box is here. So dxy, dyz, dg square. So dxy, dyz, dxy, dx square minus y square and dg square. So these orbitals located here, and so if you look at the interaction, dg square, bonding. So this is kind of bonding character. But if you look at the dxy and dyz, if you look at the structure, non-antibonding, you cannot make bonding. So these are located in high energy level. So these are antibonding. Do you understand? Okay, I want to summarize the ferrocene. So CP ring, there are 2 CP rings, so you need to make group orbital, not molecular orbital, group orbital. Because the one CP ring cannot interact with the other CP ring. We cannot say molecular orbital, just group orbital. Okay. So you can think about other metallocene. Okay, so if you think about the other metallocene, cobalt, nickel, the unique properties is the color. So ferrocene is orangey, cobalt is purple, nickel is green. If you counting the electron, these have these electrons. So unpaired electrons 0, 1, 2. So metal carbon distance is getting longer. So metal plus dissociation energy is smaller. So metal is here, cyclopentadiene is longer. The dissociation energy is small. Small dissociation. 작은. Small amount of energy is required to break down this bond. Okay, if CP ring is very close to transition metal, then we need much energy to break down. But longer, we need just this lower energy. Okay, let's go back to reaction. Ferrocene is stable because why? Because ferrocene has 18 electrons, the fully occupied electron. However, CO has 19 electrons. 19. About I'm sorry, not CO. Cobalt has 19 electrons, and nickel has 20 electrons. So ferrocene is stable, but others are not. So if you think about cobalt complex, cobalt can easily interact with I2 to make this one. So as I told you, cobalt has 19 electrons. 19. It means that cobalt want to give the electron to others to make stable 18 complex. Do you understand? I want to say in Korean. 그러니까 페로세는 18개의 전자를 갖고 있으니까 매우 안정하잖아요. 그러니까 뭐 변화가 별로 없는 거야. 근데 코발트는 몇 개 갖고 있다고? 19개. 그러니까 내가 19개 갖고 있으니까 난 18개를 가져야 안정하니까 하나를 어떻게 해? 빨리 누군가를 주고 싶지. 자, 누군가를 준다고. 전자를 누군가를 줬어. 그럼 자기는 뭐가 돼요? 전자를 잃었으니까 산화가 되는 거죠. 그러니까 자기는 산화가 되고 전자를 누군가한테 줬어. 본인은 산화하면서 다른 사람을 본인이 산화됐으면 다른 사람은 어떻게 했겠어요? 환원시켰겠지. 그러니까 뭘로 쓸 수 있다? 환원제로 쓸 수 있다라는 거죠. 네, 맞아요. 그래서 so this cobalt complex gives the electron to I2 and making 18 electron complex and 2I minus is generated. Okay, so and then cobalt complex can react with hydride to make eta 4 CP. In this case, hydride attack the carbon. This one is produced. Okay, and there are different type of metallocene, not composed by copper. I'm sorry, not composed by carbon, composed by phosphine. So, because there is no carbon, so we call inorganic metallocene. Okay, I want to say reaction of ferrocene, so you need to remember this type of reaction. Ferrocene is stable, as I told you, but ferrocene, the interaction between transition metal and CP is stable, but in CP we can make some reaction still using CP. So this ferrocene complex can react with like Friedel-Crafts oscillation. So ferrocene can attack this carbon. So if you look at the result, this result is Friedel-Crafts oscillation. So okay, look at me. So we are talking about metallocene complex. So as I told you, ferrocene is very stable organometallic complex. So in organic compound, very stable compound is benzene. So what I want to say is the ferrocene is very similar to benzene. So if benzene can Friedel-Crafts oscillation, ferrocene can do that. So you need to I suggest to you need to remember the reaction of aromatic compound. Okay. So we are talking about allyl or cyclopentadiene. So pi complex. There are many pi complex. So group 4, 5, 6, 7. These metals can make pi complex. So in next class we have talked about CO, and today we are talking about pi complex, pi ligand. So the same thing between CO and pi ligand is they can act as a sigma donor as well as pi acceptor. So they can make a strong interaction between transition metal. That's very important thing. So many transition metal has CO and CP. So there are many examples having CO ligand and pi ligand. Okay, cyclic CP. First thing is cyclopropane, but in this case, cation. You need to think like cation. Cyclobutadiene, like this. So in method A, they will give 6. Method B, 4. CP, method A, 6. Method B, 5. So if you think about method B, just 3, 4, 5, 6, 7, 8. Okay? But in case of method A, 2, 6, 6, 6, 6, 10. But in this case, we need to consider 2 minus. Okay? So in case plus, in case 2 minus. Just cyclobutadiene is just you need to distinguish in this case, if trash metal coordinate to only 2, just 2. But in this case, we want to say I cannot find the structure in ChemDraw. So in this case, just 4 carbon, all coordinate to transition metal. So 4 minus, 2 minus. Do you understand? Okay, so never mind. So at this point, we don't need to talk about this. Just only CP and benzene. Okay. Okay. Other cyclic pi system. So cyclopropene, cyclopentadiene, and cycloferrocene, and benzene. So these are examples. So 7-membrane, 8-membrane. Okay, just to, if you think about this type, okay, so actually here is anion, here is anion. Okay, so make this anion, anion. So 2 minus, 2 minus. And cyclopentadiene. Okay, cyclopentadiene, how to make it? You can make cyclopentadiene from cyclopentadiene. 그러니까 여러분들 헷갈리면 안 되는데 이게 I want to say in Korean 리간드를 설명할 때는 ani온이란 말을 잘 안 해요. 그러니까 cyclopentadiene 이라고 cyclopentadiene anion cyclopentadiene 리간드라고 하면 여러분 알아서 ani온을 생각해야 돼. 무슨 말이 이해돼요? 그러니까 굳이 내가 cyclopentadiene이라고 하면 이걸 생각해야 돼요, 여러분. cyclopentadiene 리간드다. cyclobutadiene 리간드다. 라고 하면 여러분들이 알아서 요 리간드를 생각해야 돼. 이렇게 생긴 거예요. cyclobutadiene 리간드는. 그냥 cyclobutadiene이 코디네이션 됐다. 라고 하는 거랑은 또 달라요. cyclopentadiene이 코디네이션 됐다 하면은 이렇게 요 이중결합이 두 개가 이렇게 아까 뭐 cyclooctadiene 붙듯이 그냥 그렇게 됐다라고 생각할 수 있는데 그거는 그냥 리간드고 지금 우리가 말하고는 cyclic pi 리간드. cyclic pi 리간드는 모두 다 이게 뭐가 됐다고 생각하면 되냐면 아로마틱이 됐다고 생각하면 되는 거야. 그래서 메소드 A에서 보면 4n 플러스 2 룰을 만족하죠. 2개, 6개, 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 10개. 왜? 다 아로마틱이라고 생각하니까. 이해돼요? 약간 다르다는 거. I want to say in English. So you need to distinguish cyclopentadiene, anion, and cyclopentadiene. 여러분의 반응을 볼 수 없으니까 참 답답한데 잘 전달이 되었으리라고 믿습니다. 이해되나요? 그래서 지금 So if I say cyclopentadiene or butadiene, that is just aromatic system. Okay? Okay, then how to make cyclopentadiene ligand? Cyclopentadiene ligand can generate from cyclopentadiene. So generally cyclopentadiene, if you buy cyclopentadiene, the aldol reaction between two cyclopentadiene and making this one. But if you heat it up, electrodiesel reaction is occurred to you can generate this one. So if you add sodium, this proton is released out and anion is generated, and if you add iron, you can make ferrocene. Okay, other cyclic pi ligand, benzene, and you can think 7-membrane, 8-membrane. Okay, I want to say NMR. So just carbon NMR bind to transition metal. If you think about C NMR, this carbon is shielded by transition metal. So in case of metal carbon, just length is here. But double bond, as I told you, the transition metal withdraw the electron. So the carbon is electron deficient. So the carbon, the range is very, very different. So for example, 400 or 10,000, but depend on whole structure, the chemical shift is different. How about proton? Proton is same. The chemical shift in this case, 2 shielded, so minus 7.5. But in this case, deshielded and downfield. So what I want to say is the chemical shift of C or proton is depend on the environment of the complex. Okay? Any questions? 대답도 없네. 질문 없으면 오늘 여기까지 하도록 하겠습니다. Okay, if you have no questions and comment, 하연아, 저는 하고 엄청 기다렸잖아. If you don't have any question and comment, so I want to close today's class. Okay, see you next week. Okay?